Hi, I'm Andrew, and together with Aditya,
I'm Aditya,
and one of the authors of the paper, Oleh, we will discuss this paper, Long Horizon Visual Planning, with goal-conditioned hierarchical predictors. This discussion will contribute to our survey paper, Planning with Deep Neural Networks. If you would like to learn more about this topic and our survey paper with a collection of approaches, check the links in the description and visit our GitHub repository. The cool thing about this paper is the idea of hierarchical planning approach that breaks a long horizon task into a series of short horizon tasks by placing middle points and sub-goals. Let's consider the following abstract example. We have an agent that has the goal to get to the airport, and the current location of the agent is at home. We can split this high-level action to get from home to the airport by introducing a single sub-goal. For example, to get to the train that connects the home and the airport. Now we can recursively repeat this process and split again this high-level action to get to the train from home by introducing a sub-goal to get to the train station. Such an approach seems to be very natural for human-like planning, and this paper proposes an attempt of technical implementation of this idea. Although the datasets and problems used in this paper look more like a toy example, the overall idea of generating middle point sub-goals seems to be promising, and therefore let's discuss technical implementation and constraints of this approach. So here we can see some examples of the performance of this approach. In the first environment, we have a maze navigation where we have 9 and 25 rooms. And the agent gets 2 images as current state and the goal state, and it has to plan a sequence of intermediate states in this maze and then navigate using this planned sequence of intermediate states. Simply put, in this visual foresight example, the model is we have a state, then we have a neural network model that predicts the next state. This state can be a latent representation obtained with an encoder from an input image. Later, the new predicted state can be decoded with a decoder back to an image. Goal-conditioned predictor is a different type of architecture where we feed into the network state and desired goal to achieve. Usually it's been concatenated, and neural network model outputs the next state. Thus, for every point in this maze, we feed into the network this current state, the goal, and it predicts next state. And this is a iterative process. We feed again new state and it predicts next state, conditioned by the goal. This paper highlights a technical implementation of hierarchical goal-conditioned planning. So simply put, the difference is that we feed again the state, the current state and goal into the network. And instead of predicting the next state, the network outputs the prediction of the intermediate state, which should be somewhere in the middle of the trajectory. So if we imagine that this is a start and this is a goal, then using these 2 pieces of information, network learns to predict the state in between. And we can repeat this process using these 2 states. We can predict the intermediate state and the same here. And we can continue until we fill this chain of states such that we have a smooth sequence of frames, which can be a video prediction or a path planning in this kind of maze. In this work, authors compared 2 goal conditions predictors. The first one, flat, uses 2 states, start and goal, to predict next step towards the goal. And it can recursively update the start state and predict the next state until the agent reaches the goal. The second goal condition predictor is hierarchical. It also takes as an input start and goal states, but instead to predict the next state towards the goal, it learns to predict the middle point on the path between start and goal. So in other words, it recursively halvens the trajectory by predicting middle point subgoals until we have a smooth sequence of states between start and goal. So both flat and hierarchical goal condition predictors can produce a sequence of subgoals between start and goal states. However, the hierarchical one has a potential to produce trajectories with a lower cost than the flat goal condition predictor. This is possible because we can sample middle point candidates using this stochastic component of the predictor, and then estimate cost for each of the candidate, and then select one with the lowest cost. This cost function was also trained by supervised learning based on expert trajectories.
Cost function is actually the distance traveled by the agent. The general idea is that we have this cost estimator that you can predict the cost from the latent state. So it doesn't have to be the Euclidean distance. In fact, it's not good for it to be the Euclidean distance. In general, if you have some kind of supervised metric like the length that the agent has traveled, you could use that as a cost, and you can learn that from your trajectories. Or you could use the time that it takes the agent to reach a particular goal. And that's the cost that makes the most sense, because the time to reach a particular goal is what you want to minimize in general. I have some newer paper that uses that. I don't quite remember what this paper uses.
So the hierarchical goal condition planning is a promising direction. However, when we work with real data, it becomes not so simple as there are many real-world constraints. Therefore, authors also modified this architecture in a more complicated one, which tries to deal with these limitations and constraints. Other than that, the main idea of this hierarchical goal conditioned planning or prediction can be as straightforward as this example. After the predictor generated a smooth sequence of subgoals, the approach uses a trained inverse model to control the agent in this maze navigation task. This inverse model was also trained via supervised learning. The inverse model takes as an input two sequential states and produces an action that connects these two states. In the second type of environments, we have a stable view environment. For example, there is a video of a human navigating in a room, and camera is stable, and only the person is moving from one place to another. So the first row is a ground truth, and the second row, that's what the model can achieve in predicting the intermediate states when it gets as an input starting point and the end point. And all intermediate states are being produced by the planning network. So there are some distortions, but in general, the trajectory of a human looks quite natural. The same for a pick and place environment. The first row is a ground truth. The next two rows are produced by the current approach. This one is using a hierarchical planning, and the next one is without hierarchical planning. And the last two rows are comparison to other methods. So when trying to implement goal-conditioned hierarchical prediction and planning architecture, we can encounter the following problems. First of all, it's a supervised learning approach. That means that we need expert trajectories. For the 2D maze navigation example, they used probabilistic roadmap planner to collect the expert trajectories. And for the human and pick and place datasets, these were a sequence of videos. This implies that actually this approach will not work for unknown environments where exploration is needed. Because if we have some random trajectory, which will have a lot of noise and probably will not lead to a goal, because it's a supervised learning approach, it will be hard to say which of the points in this trajectory should be between start and goal. For example, if the agent starts here and makes a lot of random movement around the start point and then suddenly comes to the final point, the intermediate point will be somewhere in this random exploration part. So that will be a not useful signal for training such hierarchical planning approach. Therefore, expert trajectories should be clean and highlighting the best performance. As a side note, there are goal-conditioned approaches in reinforcement learning. For example, here, there is a task of in-hand manipulation of an object, and this object has a current state, and it has a goal state. And we can use a deep deterministic policy gradient approach, which is an actor-critic approach, where we have a state representation as a vector, which incorporates information about the hand and about the object. And we have another vector that represents the goal. We can concatenate these vectors and feed to the policy neural network, which produces an action. We can concatenate this action with the same state representation and the same goal. And there is a second critic neural network that predicts the value. There's a single one-dimensional prediction of the value of state-action pair. So here, in this approach, critic using deep reinforcement learning is trying to map all state-action pairs into the value. And then by optimizing the policy neural network for every state conditioned by goal, we get actions for these actuators. So to conclude, this long horizon planning approach is not an alternative to reinforcement learning because the current technical implementation doesn't work for exploration. Instead of exploration, we need clean expert trajectories. So besides this supervised learning constraint, another constraint is different path alternatives. For example, we can have this path, which is valid together with a different alternatives, which is also a valid path. So that means that if we feed as an input these two state and goal input information, the network has to be able to learn to predict two very different states, which are a valid example of intermediate states between these two goals. Therefore, if we have our original static example where we have a state and a goal, and if there is no stochasticity, the network will always predict the same intermediate output state. So if we provide for the same state and goal different labels, the network may just learn none of them. Just to clarify, the term labels comes from the concept of supervised learning, where we train a neural network model by providing input and label pairs. So for example, here we encode these two image patches, start and goal, into two latent vectors S and G. Then we feed these two vectors S and G into a neural network model as an input, and the network predicts the latent vector M that can be decoded into the image patch, which is the middle point of the trajectory between start and goal. So here, this middle point patch we can call label, and patches S and G are inputs to the model. So if we provide for the same state and goal different labels, the network may just learn none of them. In this implementation, this problem was mitigated by using a stochastic component. So here we are doing sampling. That means that we have our start and goal vectors, latent representation. We can concatenate them and feed into the neural network. And then instead of producing a specific mapping value from state goal pair to some intermediate state representation in the latent space, we have a Gaussian sampling around the mean value. This is a two-dimensional example, but it can be a n-dimensional Gaussian sampling. So now each time when we have two different label alternatives, for the same input vector, we have a training signal that will place these alternatives somehow slightly apart from each other. But nevertheless, they have to be in somewhere near the mean value of this distribution. Therefore, one hypothesis is that this is kind of a clustering mechanism that for a given start and goal points in latent space is trying to form a cluster of points in the same latent space, which can belong to different trajectories. So potentially it could be even a trajectories clustering approach, especially because there are not so many path alternatives in a given maze. as you can see here, or for human or pick-and-place video demonstrations. Another problem that comes from the supervised learning nature of this approach is the alignment of trajectories. If we have, let's say, the same path, but we have many different trajectories in this path, let's say after 50 timestamps, trajectory 1 will be here, but for example, trajectory 2 will be here, which have completely different visual representations. So again, we have the same problem that we have start state representation, goal state representation. We have even the same path, but because of the difference in temporal alignment or velocities of the agent, the network will need to deal with the prediction of different intermediate states. So in one case, it can be this patch that represents the middle point, and in the other trajectory, which has the same path, this middle point of the trajectory can be represented by this patch. And these are two visually quite different representations. So partially, this problem can be solved again by this stochastic component. But additionally, an adaptive binding approach was introduced for better alignment of true sequences for dynamic time warping. If there are two sequences which reach the same destination at different time steps, we can use dynamic time warping approach to synchronize corresponding states in a sequence.
Dynamic time warping basically allows us how to align two signals of different durations. The dynamic time warping algo takes in two signals and outputs something similar as shown in the figure on the right. The gray lines tell us which points on one curve correspond to the points on the other curve. In the paper, it is mentioned that certain alignments, such as the ones that violate the ordering of the sequence, which are produced by the tree, and the evidence are forbidden. So to compare such sequences, we have used dynamic time warping.
Another problem is an ambiguity of state representation, namely because we take visual patches. Here they all unique. We have it, in this case, 25 rooms example, and all rooms have unique textures. If we would have several rooms with the same texture, that would introduce some ambiguity. Namely, if, for example, these two rooms would have the same color, then these two labels are the same, but apparently they are used for different inputs. For example, if that would be a start, and would be the goal, that would be a valid intermediate point prediction. And in the second case, if that would be a start point, and that would be a goal point, then that would be a valid intermediate state. So we have again the situation where we have different pairs of state and goal, but the same label, if that would be the same color. To avoid this situation, all rooms have a different texture. This is a common problem, and for example, another approach, semi-parametric topological memory for navigation, which uses a 3D environment and learns to navigate to a goal, which you can see here. As you can mention here, we also have all textures are unique, at least textures of walls. So that's one of possible limitations and a challenge for future improvements of planning approaches with deep neural networks. Another challenge to mention is the generalization, namely if we have, for example, two paths, two experiences, and now we want to take this start and this goal. Can we predict the paths between start and goal that can combine experiences from different trajectories? In the current paper, there is no explicit study on this generalization property, but there is a chance that it can handle this generalization. If you know a paper or approach that can handle this problem of generalization, leave it in a comment below. So to conclude, there are the following challenges. So first, good quality expert trajectories are needed for the supervised learning setup of this approach. Then the generalization of expert trajectories. Then handling of alternative paths, which is solved by the stochastic component of the network. Then ambiguity of visual observations, which is not very clear whether this approach can handle this. and dynamic time warping included in the code implementation of this approach. Let's discuss this main figure about the architecture of goal condition predictor. If we take this maze example, then this will be a patch of a top-down view on the maze, and that will be a second goal patch of the maze. Then it's been encoded into latent space, which has dimension 128, and that's the same encoder. And the same latent state representation can be later decoded back to the reconstructed image of an intermediate state using the decoder. Here you can see skip connections. So here we have the decoder module and we have this skip connections, which also makes for us some problems to understand why do we need skip connections? Because our assumption is that if we have like a unit, for example, that makes totally sense to have skip connections because it like predicts usually a mask, and this mask needs some low-level features.
You're talking about the maze example, right? But we actually run on 4 different datasets, and we run on some other datasets as well. But the ones in the paper, I agree with you that for the maze it wouldn't help, but it does help a lot for the other examples.
Yeah. So that's usually situations where you have stable background and something is moving on the screen, right?
Yeah, the datasets where it helps is mostly when you need to copy the background. But also if the background kind of changes slowly, it would still help you significantly. So if the camera motion is less, it would help you. If it's a self-driving car and you want to reconstruct the entire image, I think it would still help you. You would just need to set it up in a more clever way. You would want your skip connections to so the hierarchical skip connections wouldn't work, right? Because you're right. Because if you're predicting the middle frame, that's very far away. Skipping any low-level features won't help. But if you're predicting sequentially, you actually would benefit a lot from skip connections because if you just are doing one-step prediction, all of your skip connections naturally still carry very relevant information, and it's much easier to adapt. For hierarchical prediction, it wouldn't help you that much. The learned prior is only used for evaluating the KL divergence. So it's not shown in the image because the image only shows generation. It doesn't show the KL divergence. But you can think about it as being part of the variational LSTM as well.
Okay.
Whereby variational LSTM, I just mean the VRNN, but we didn't want to call it that. We decided to call it variational LSTM. Inference is also not shown because it's a part of training, and the architecture, I believe, only shows the generation. The inference network is as normally in your variational autoencoder, you would have an inference network that's only used for training, not for test. And the existence predictors predict whether the tree ends right now or not. So it's just trained with supervised learning. If the tree ends, the output puts 1, and if it doesn't, then it outputs 0, or the other way around.
Now coming to the variational tree LSTM, the output of the LSTM actually goes into the decoder. Here we can see the architecture of the hidden tree LSTM and the MLP LSTM initializer.
So zoom in of this var LSTM unit, we can see here. If we, at the very beginning, and this is a start and this is a goal, then we just encode that in latent representation and feed that into this unit here. Then we concatenate them. That means that here we have 256 dimensional vector, which goes directly to the LSTM cell. And this also goes into multi-layer perceptron, which has a variational component, stochastic component. Then we have 256 dimensional mean values and 256 dimensional standard deviation Gaussian values. So that will be a vector of 512 that splits into mean and stochastic values. And then we do sampling. Our sample is equal to mean value plus some random number times standard deviation value. And we do that for every dimensions. Thus, we have a sample of 256 values. Then probably we are concatenating these two vectors. One is concatenation of two latent vectors, and other is sampling a result. Thus, the input to this tree LSTM is, according to this picture, has to be 512 dimensional.
A purely deterministic latent variable might not be able to model the variation in the data, while a purely stochastic one might lead to optimization challenges. So here, the latent state has been split into two parts. HT is the deterministic state and does not require the inference since it can be simply computed from the observation data. And ZT is the stochastic component, which we can get by leveraging the amortized variational inference with an approximate posterior. The interesting thing about the stochastic component is that it captures just the difference between all possibilities in the particular hierarchical prediction sequence.
They have different code implementations, and some of them incorporate additional contextual information which is not covered in this figure, so it can have a different dimension of the input of the LSTM. They have 3 layers of LSTM cells, which outputs a latent state of the intermediate point in the trajectory between start and goal. Also, we have skip connections from LSTM, and most probably we also have a multi-layer perceptron on these connections, but the exact implementation remains slightly unclear. And then we recursively repeat this process until we come to a sequence of intermediate states. And because it's a supervised learning approach, we have an expert trajectory, we have this tree rollout, and at the end we have a sequence of latent states, which should be sequential. And then we have the ground truth labels of this path and predicted rollout of a sequence of latent states. And now they just need to correspond to each other. Basically, the training signal comes from reconstruction of an image patch from a latent state representation. So one more time, as an input, we have 2 images. These images are being encoded into latent vectors. Then we have a machinery that produces a tree of latent states. Then we take these all latent states and put them into a sequence. For example, that will be first time step, second, third, fourth, fifth, and so on. So this is our path that we generated. And we have latent states for all these patches. And now we have the expert trajectory. And we also can extract these ground truth patches. And now the decoder has to reconstruct these visual patches using these latent state representations. And this supervised learning setup provides these training signals for the complete architecture. If you would like to learn more about this topic and our survey paper with a collection of approaches, check the links in the description and visit our GitHub repository.